So, let's go. Number 1. Magnetars, where magnetism rewrites chemistry. Picture a dead star, city-sized, maybe 20 kilometers across, spinning, and wrapped in a magnetic field 1 quadrillion times stronger than Earth's. That's a magnetar. And at that field strength, the rules you learned in chemistry class stop working. Hydrogen atoms, normally little round clouds, get squeezed 200 times narrower than usual. They become needles. Long, thin, impossible needles of matter that shouldn't exist. The surface of a magnetar is covered in chains of these needle atoms, stretched into weird polymers that no lab on Earth could ever produce. But it gets worse. The magnetic field is so intense that photons, particles of light, start doing things light isn't supposed to do. X-ray photons split in two, or 2 photons merge into 1. The empty vacuum around the star starts behaving like a crystal, bending light in different directions depending on its orientation. The void itself becomes a lens. And here's a detail that still breaks my brain. The energy stored in that magnetic field is so dense that the field itself has mass. Through E equals mc squared, the energy density of a magnetar's field is 10,000 times heavier than lead. The magnetism weighs more than metal. You do not want to be near one. At 1,000 kilometers, roughly the distance from Los Angeles to Portland, a magnetar's field would rip the electrons from every atom in your body. You wouldn't burn, you wouldn't freeze. You'd be disassembled into a cloud of individual ions. Your body's molecular bonds would simply stop existing. You'd become a mist of single atoms stripped bare, drifting in magnetic wind. And they're not quiet about it. On December 27, 2004, a magnetar called SGR 1806-20 went off. In 1/5 of a second, it released as much energy as the sun produces in 250,000 years. From 50,000 light years away, the other side of the galaxy, that burst partially ionized Earth's upper atmosphere. It overwhelmed NASA's Swift telescope. A spacecraft literally designed to stare at gamma-ray bursts had its detectors completely saturated. If that magnetar had been within 1,000 light years of us, it could have triggered a mass extinction, and we know of only about 30 of them in our galaxy. There could be more. There are probably more. Oh, and scientists recently found one being born. A massive star called HD 45166, the most magnetic massive star ever discovered. It's a prime candidate to collapse into a magnetar, a ticking bomb wrapped in 43,000 Gauss of magnetic field, waiting to become one of the most violent objects in the universe. The scariest part about magnetars isn't the death. It's that chemistry, the thing that holds you together, the thing that makes water wet and iron hard and DNA possible, just doesn't apply anymore. The rules that build everything you've ever touched get overwritten by a magnetic field. And we haven't even gone inside yet. Number 2. Neutron star interiors, where atoms cease to exist. That magnetar you just met? Let's go through the surface. The outer crust is iron, compressed into a crystal lattice so tight it makes diamond look like tissue paper. Below that, the pressure gets so extreme that atoms can't hold themselves together anymore. Electrons get crushed into protons. Everything becomes neutrons. And a single teaspoon of this neutron material weighs about 1 billion tons, roughly the same as Mount Everest. That's not a metaphor, that's the math. But keep going deeper, and things get genuinely alien. About 1 kilometer below the surface, the pressure is so immense that the neutrons themselves start deforming. They get squeezed into shapes, blobs, rods, sheets, tubes. Scientists call these shapes nuclear pasta because the phases look like gnocchi, spaghetti, and lasagna. It sounds like a joke, but the name stuck and the physics is dead serious. Nuclear pasta is the strongest material in the known universe, 10 billion times stronger than steel. A team ran the largest computer simulation ever attempted of a neutron star crust, 2 million hours of processing time, the equivalent of running a laptop for 250 years, and when they tried to break the pasta, they couldn't. Nothing in any simulation or any equation we have describes a material this tough. Mountains on a neutron star, limited by the breaking strain of this crust, are centimeters tall. Not kilometers. Centimeters. And even those tiny bumps spinning at 716 rotations per second on the fastest pulsars might be generating gravitational waves we could detect. Now go deeper still, into the inner core, and nobody knows what's there. The leading idea is that at those densities, 5 times denser than an atomic nucleus, neutrons themselves break apart. Quarks spill out of their containers. They stop being bound inside particles and start flowing freely, possibly forming something called color superconducting quark matter. It's a state of matter where quarks pair up kind of like electrons do in a superconductor, except instead of conducting electricity, they conduct color charge, the force that holds atomic nuclei together. Now here's what's confirmed and what isn't. The nuclear pasta, peer-reviewed, simulated, published. The quark matter, a major 2020 study in Nature Physics found strong evidence that the cores of the most massive neutron stars behave like deconfined quark matter. But confirmed? No. We can't crack one open. The speed of sound inside may exceed 60% of the speed of light, over 180,000 kilometers per second, 18,000 times faster than sound in diamond, and even that is still a calculation, not a measurement. Everything about these interiors exists at the boundary of what we know. The matter is real. Our understanding of it is a work in progress. And the deepest, strangest thing about neutron stars isn't any single fact. It's that there are objects in the sky right now, small, dense, spinning, that contain matter in states that literally do not exist anywhere else in the observable universe. Not in any lab, not in any particle collider, not in the Big Bang anymore. Only here. Only under pressures we will never recreate. Now, you've seen what extreme objects do to matter. Let's talk about what happens when there's nothing there at all. Number 3, the quantum vacuum, where nothing pushes back. Take everything out of a region of space, all the matter, all the radiation, every atom, every photon, every particle. Make it perfectly, completely empty. You're not done. Because that emptiness has energy. It has force. And if you put 2 metal plates close enough together inside it, the nothing will push them toward each other. This isn't philosophy. It was measured. In 1948, a Dutch physicist named Hendrik Casimir realized something unsettling about quantum mechanics. The uncertainty principle says you can never have exactly zero energy in any region of space. Even in a perfect vacuum, particle-antiparticle pairs are constantly flickering into existence and vanishing again. Too fast to measure individually, but real enough in aggregate to have consequences. Between 2 uncharged metal plates placed nanometers apart, only certain wavelengths of these virtual particles can fit. Outside the plates, all wavelengths exist, so there's more pressure on the outside than the inside. The nothing pushes. In 1996, a physicist named Stephen Lamoureux measured the force. It matched the prediction within 5%, less than a billionth of a newton, almost imperceptibly small, but real. Emptiness has opinions about where metal should be, and it gets weirder. In 2008, researchers demonstrated a repulsive version of the same effect, the void pushing plates apart instead of together. And in 2011, a team in Sweden simulated a mirror moving at 5% the speed of light using a superconducting circuit, and the vacuum responded by producing actual, real photons. Shake nothing hard enough and it gives you light. There's a deeper problem here, though. When physicists calculate how much energy the vacuum should contain based on quantum field theory, they get a number. When they compare that number to the actual energy density of the universe, the thing driving its accelerating expansion, the prediction is off by a factor of 10 to the power of 120. That's not a rounding error. That is often called the worst prediction in the history of physics. And nobody knows how to fix it. The vacuum isn't empty. It's the quietest version of something incredibly loud. And the fact that we don't understand why it's quiet instead of screaming is one of the deepest unsolved problems in science. Every entry on this list, every magnetar, every black hole, every void, exists inside of this seething, impossible nothing. The space between the things is doing something too. Now let's go somewhere that takes that emptiness and scales it up to something terrifying. Number 4. The Bödes void, where the universe forgot to build. There's a region of space about 700 million light-years from Earth in the direction of the constellation Bödes that contains almost nothing. It's roughly spherical, about 330 million light-years across, and inside it there are maybe 60 galaxies. 60. In a volume where you'd expect thousands. It was discovered in 1981 by an astronomer named Robert Kirshner who was mapping galaxy positions using redshift data. He found a blank spot, not an artifact, not a gap in the data. An actual region of the universe where the cosmic web, the foam-like structure of galaxy filaments and clusters that makes up everything, just isn't. Here's what gets me. If you lived on a planet inside the Buddha's void, your night sky would be almost empty. No Milky Way, no neighboring galaxies visible to the naked eye. The nearest galaxy might be tens of millions of light years away. A civilization that evolved there might never develop the concept of other galaxies until they invented radio telescopes. They look up and see blackness and think that was normal. Our local group of galaxies is about 10 million light years across. You could line up 33 of them end to end and barely span the Buddha's void. If the Milky Way were a marble, this void would be a sphere nearly a mile wide. Nobody fully agrees on why it exists. The standard model of cosmology says voids form naturally. Tiny density differences from the early universe get amplified over billions of years. Matter flows toward dense regions. Empty regions get emptier. But the Buddha's void is big, uncomfortably big. Some researchers think it might be several smaller voids overlapping. Others call it a cosmic scar, the imprint of something rare and unknown from the early universe. And then there's the really weird part. A separate, even larger void, the Eridanus supervoid, 1.8 billion light years across, lines up with a mysterious cold spot in the cosmic microwave background. The oldest light in the universe has an unexplained cold patch, and there's a giant empty region sitting right in front of it. But a 2025 analysis found the void isn't deep enough to explain the temperature anomaly. The odds of the cold spot being random chance are about 1 in 2,000. Some explanations for it are normal physics. Others include topological defects from the early universe. And one, and I want to be clear, this is speculative, one proposes it could be a bruise left from a collision with another universe. Nobody knows. The void just sits there, being empty, being enormous, being unexplained. Now let's visit somewhere that makes a little more sense. 5 specific spots where physics does something almost friendly. Number 5, Lagrange points, where gravity cancels out. In any system where 2 massive objects orbit each other, the Sun and Earth, the Earth and Moon, Jupiter and the Sun, there are exactly 5 points where all the forces balance. Gravity from both objects plus the centrifugal force of the rotating system add up to 0. A small object placed at one of these points just stays there. Relative to the 2 big objects, it doesn't move. These are the Lagrange points. 3 of them sit along the line connecting the 2 bodies. Between Earth and the Sun, about 1.5 million kilometers sunward, is L1, where the Sun's gravity and Earth's gravity partially cancel, letting an object orbit the Sun at the same pace as Earth despite being closer. On the other side, the same distance past Earth, is L2, where Earth's gravity tugs a slower object forward to keep pace. And opposite the Sun from Earth sits L3, the counter-Earth point. L1, L2, and L3 are unstable. They're like balancing a ball on a hilltop. Any tiny push and you drift away. The James Webb Space Telescope sits in a halo orbit around L2 and needs periodic engine burns just to stay put. But L4 and L5, 60 degrees ahead of and behind Earth in its orbit, are stable. They're bowls, not hilltops. If you nudge an object there, the Coriolis force curves its path into a kidney bean-shaped loop around the point, and it stays. Jupiter has thousands of asteroids trapped at its L4 and L5. They've been there for billions of years. Earth has one too, a small Trojan asteroid discovered in 2011, drifting along in our orbit 60 degrees ahead of us. Quietly parked. In 1975, a group of space enthusiasts founded the L5 Society with one goal: building permanent human habitats at Lagrange points. Their founding principle was to disband the society in a mass meeting held at L5. They never got there. The society merged into the National Space Society in 1987. But the dream wasn't crazy. We park billion-dollar telescopes at these points right now. They're real places where gravity takes a breath, where the math lets you rest. Now let's go somewhere gravity doesn't rest. Somewhere gravity grabs space-time by the throat and drags it in circles. Number 6. The ergosphere, where space itself is dragged. When something massive rotates, it doesn't just curve space-time, it drags it like a bowling ball spinning in honey, pulling the honey along with it. Einstein hinted at this in 1913. Two Austrian physicists named Lenzi and Thüring worked out the math in 1918. And in 2004, NASA launched Gravity Probe B, four of the most precise gyroscopes ever built orbiting Earth, and measured the drag. Earth's frame dragging effect is tiny, 37 milliarcseconds per year, barely measurable. But it's real. Our planet is twisting space. Now scale that up to a supermassive black hole spinning at a significant fraction of the speed of light. Around a rotating black hole, there's a region outside the event horizon called the ergosphere. It's the zone where space-time is being dragged so fast that standing still becomes physically impossible. Not difficult. Impossible. You could point your engines directly away from the spin and fire at maximum thrust, and you would still be carried in the direction of rotation. Space itself is moving beneath you faster than you can push against it. In December 2025, astronomers watched this happen in real time. 400 million light-years away, a star wandered too close to a supermassive black hole and was ripped apart. The debris formed a spinning disk, and jets of matter shot out at nearly the speed of light. But the disk and the jets were wobbling, together, in sync, on a 20-day cycle. The black hole was twisting space-time, and that twist was wobbling the entire system like a spinning top, dragging water into a whirlpool. It was the most direct evidence ever recorded of a black hole dragging the fabric of reality. And here's the beautiful part. In 1969, Roger Penrose figured out that you can steal energy from this process. Enter the ergosphere. Split an object into two pieces. Let one piece fall into the black hole against its spin. The other piece escapes with up to 129% of the original energy. You're mining the black hole's rotation, taking energy from the spin of space-time itself. The ergosphere is the first place on this list, where a space isn't a stage. It's a participant, it moves, it drags, it has momentum, and it's only a warm-up for what's on the other side of it. Number 7. The event horizon, where time and space swap places. The event horizon of a black hole is not a wall, there's nothing there. No surface, no barrier, no membrane. If you were falling toward a supermassive black hole, something like TON 618, 66 billion solar masses, event horizon so wide that light takes days to cross it, you could pass right through the event horizon and feel absolutely nothing. But something has happened to you that can never be undone. The event horizon is the point where the escape velocity equals the speed of light, and past it, all the math goes sideways. In the equations of general relativity, the coordinate for time and the coordinate for radial distance literally switch roles. Inside the horizon, moving forward in time means moving toward the center. Every direction in space points at the singularity. The outward direction, the one that used to mean away, becomes the past. You can't turn around. Not because something's stopping you, but because away from the center is no longer a direction in space. It's a direction in time, and you can't go backward in time. Here's what it would look like. Your friend, watching from a safe distance, sees you approaching the horizon. You slow down. Your light stretches redder and dimmer. Eventually you appear to freeze, a fading, reddening image that never quite crosses over. To them, you're stuck there forever, a ghost at the boundary. But you don't experience that. You fall right through. And at the moment of crossing, all the light that will ever reach the horizon from the outside universe gets compressed into a brilliant ring around you. A flash of everything that was ever going to arrive. Then, depending on the black hole, darkness, or the glow of other falling things. Just outside the event horizon, at 1.5 times the Schwarzschild radius, there's the photon sphere, where light itself orbits the black hole. If you could hover there and look straight ahead, you'd see the back of your own head. Light leaving your skull would circle the black hole and come right back to your eyes. And time is doing something deeply uncomfortable. 1 hour near the event horizon of a supermassive black hole can equal years on Earth. This isn't speculation. GPS satellites already correct for gravitational time dilation from Earth's comparatively gentle gravity. 38 microseconds per day. Near a black hole, that effect becomes extreme. The event horizon is the place where the geometry of reality gets rearranged so thoroughly that the concepts forward and outward stop meaning what they've always meant. It doesn't kill you with force. It kills you with geometry. And at the center of everything inside it, there's something even worse. Number 8, black hole singularities, where the math goes to infinity. Every black hole, according to general relativity, has one. A point of zero volume and infinite density. Not a big number. Infinity. The equations of Einstein's theory produce a result that is genuinely meaningless. A divide by zero error in the fabric of reality. In 1965, a mathematician named Roger Penrose proved that singularities aren't a quirk of simplified models. They're unavoidable. If enough mass collapses past a certain point, general relativity guarantees a singularity will form. He won the 2020 Nobel Prize for this, and here's what that means. Physics has a theory, general relativity, that makes stunningly accurate predictions about gravity, orbits, GPS timing, gravitational waves, black hole shadows. It works everywhere we've tested it, everywhere except at the single point it says must exist inside every black hole. There, its own math breaks. This is the only entry on this list where the laws of physics don't just produce weird results, they produce no result. The theory points to a place and says, I cannot describe this. Now, physicists are trying to fix it. In February 2025, a team described for the first time how black holes without singularities could form from pure gravity. No exotic matter required. Their approach uses modifications to Einstein's equations that quantum gravity predicts naturally. If that holds up, singularities might be an artifact of an incomplete theory, not a feature of reality. Penrose himself proposed something called cosmic censorship, the idea that nature always hides singularities behind event horizons, so the error never leaks out. 50 years later, it's still unproven. But a 2024 study showed that quantum mechanics seems to support it. Quantum effects can dress naked singularities, wrapping them in horizons. And there's a genuinely unsettling finding from 2024. When physicists modeled quantum black holes, they found 3 distinct categories. In 2 of them, the singularity goes away. Quantum gravity resolves it. In the 3rd category, the singularity survives. Even quantum gravity can't fix it. Some black holes might simply contain a place where physics doesn't work. Loop quantum gravity says singularities bounce. Compressed matter hits Planck density and erupts outward. String theory says they're fuzzballs, tangled knots of strings with no sharp center. Other models say singularities never form at all. None of these have been observationally confirmed. We are firmly in the territory where the smartest people in the world are guessing, educated guessing, constrained by math, but guessing. The singularity is the only place on this tour where we're not saying physics does something strange. We're saying physics throws up its hands. And what comes next makes that worse. Because the last 2 entries aren't about places that exist inside objects. They're about things the math predicts or the universe is doing that we can't explain at all. Number 9. White holes, where time runs in reverse. General relativity has a property that most people don't think about. Its equations work the same forward and backward in time, which means every solution that describes something falling in also describes something coming out. A black hole is a region nothing can escape. Flip time. Now you have a region nothing can enter. Matter and light can only come out. A cosmic fountain erupting into existence, repelling everything that approaches. That's a white hole. And it's a perfectly valid solution to Einstein's field equations. Oppenheimer and Snyder identified them in the 1930s. But let's be completely clear, everything I just said is math. No white hole has ever been observed. No known physical process creates one. They would violate the second law of thermodynamics, and they'd be wildly unstable. Even the cosmic microwave background brushing against one would probably cause it to collapse or explode. So why are they on this list? Because physicists keep finding reasons to bring them back. Loop quantum gravity, one of the leading candidates for a theory that unifies gravity and quantum mechanics, predicts that black holes don't end. They bounce. Matter falls in, compresses to the highest density the universe allows, and then erupts back out as a white hole. The bounce takes microseconds from the inside but billions of years from the outside because time near a singularity is warped beyond recognition. A 2025 study went further. It proposed that dark energy, the mysterious force expanding the universe, acts as a kind of clock inside black holes. And with that clock running, the singularity gets replaced by a transition zone. The black hole becomes a white hole. A 2024 paper proposed something even stranger, that real black holes might be a quantum superposition of black and white horizons simultaneously. A gray hole, neither fully trapping nor fully releasing, both at once. Some physicists have pointed out that the Big Bang itself looks an awful lot like a white hole. Everything emerging, nothing going in. The ultimate eruption from a singularity. And Carlo Rovelli, that's one of the founders of loop quantum gravity, proposed in 2018 that tiny remnants of black to white transitions might be floating through the universe right now, too small and dim to detect, contributing to dark matter. None of this is confirmed. But the math keeps pointing here, and every few years the pointing gets more specific. White holes are the universe's ghost story. Allowed by the equations, demanded by some theories, seen by nobody. They might not exist. But if they do, they're places where time itself reverses, where the arrow that always points from past to future gets flipped, and what fell in comes back out. Now, the last one. Number 10. Dark flow, where the universe is being pulled somewhere impossible. In 2008, a NASA scientist named Alexander Kashlinsky found something that shouldn't exist. He was studying galaxy clusters, enormous collections of galaxies bound together by gravity, using data from the WMAP satellite. He was measuring a subtle effect. When hot gas inside galaxy clusters scatters photons from the cosmic microwave background, it creates tiny temperature shifts that reveal how fast each cluster is moving. The effect is so small, it's never been detected in a single cluster. You need hundreds. Kashlinsky had about 700, and when he mapped their motions, they were all going the same way. Hundreds of galaxy clusters spanning billions of light years, all moving together at roughly 2 million miles per hour toward a patch of sky between the constellations Centaurus and Vela. By 2010, his team had expanded the sample to over 1,000 clusters. The flow persisted out to 2.5 billion light years, same direction, same speed, same. Independent of the universe's expansion. This should not happen. The standard model of cosmology says the universe is the same in every direction on large scales. No preferred direction, no cosmic current. Bulk motions of galaxy clusters should get weaker with distance, not stay constant across billions of light years. Kashlinsky called it dark flow, and his quote about it still haunts me. We can only say with certainty that somewhere very far away the world is very different than what we see locally. Whether it's another universe or a different fabric of space-time, we don't know. Something beyond the observable universe, past the edge of everything we can see, appears to be gravitationally pulling on everything we can see. I need to be honest here. This is contested. The Planck satellite team ran their own analysis in 2013 and said they found no significant signal. Kashlinsky's team maintained their result, expanded it, and stands by it. The debate is not settled. This might be real, it might be a measurement artifact, but if it's real, picture it, every galaxy cluster within 2.5 billion light years. Thousands of them, each cluster containing hundreds or thousands of galaxies, each galaxy containing hundreds of billions of stars. All of it, every bit of it, being dragged in the same direction at 2 million miles per hour, towards something no telescope can see, something that might predate inflation, something that might be structure from before the universe as we know it even began. Or something from a completely different universe pressing against ours gravitationally. Nobody knows. The laws of physics didn't break at any of these 10 places, that's the thing. Every magnetar, every singularity, every void, every impossible vacuum, the physics was working the entire time. Producing results that are correct and calculable and completely alien to anything evolution prepared us to understand. The universe wasn't built for human intuition, it was built by mathematics, operating at scales and densities and energies that our brains were never designed to process. We evolved to track fruit and avoid predators on a warm savanna. And then we pointed our telescopes at the sky and found places where atoms become needles, where nothing pushes metal, where time becomes space, and where the entire observable universe is sliding towards something invisible. The laws of physics don't break, they just stop pretending to be simple.